All right, so just a reminder that assignment 5 is posted for BUDA 450 and accounting 493C. It'll be due at midnight this Friday. Just a reminder too, especially if you've been struggling more recently with our markdown files and knitting them and everything. Kristen, I know, has virtual office hours on Wednesday mornings and Thursday afternoons. That information is posted on the Zoom information tab of eCampus. And then I will also be in the office Wednesday morning for in-person office hours, or you're welcome to reach out for virtual ones. I know Brad's the same. I think his office hours are posted for Monday and Wednesday mornings, but he's available for virtual, so don't forget about that. I think our plan is to get through the advanced regression module this week and next, and then we'll have one more assignment that we give you that'll be due before Thanksgiving break. I think that we'll have 2 more assignments due before Thanksgiving break. I keep thinking Thanksgiving's coming up sooner than it is, but so yeah, we'll get through this module this week and next and have another assignment due. And then the last week of content before we'll get into some time series and do some data viz and Tableau before Thanksgiving. When we come back, we don't have a ton more. But the other thing that I wanted to mention today that's kind of on the horizon that potentially, Samantha, yeah, so how many assignments are left? We have 9 assignments total. So you're about halfway through. So you have this one and 4 more. I will say we expect the last assignment not to be, it won't necessarily pertain to module content. It'll be more kind of like reflective on your all's part, a little bit more of a qualitative assignment. So it should be an easy A. So yeah, good question. The other thing that I wanted to mention, and this may not pertain to all of you, but certainly we think that there are some in the audience that this will pertain to. So as some of you know, Brad and I work with the Joint Interagency Task Force, which is the group in West Virginia responsible for the COVID response for the state. Brad serves as the chief data scientist and I serve as the senior data scientist for that group. We have secured some additional funding through next year that's going to allow us to financially support a graduate assistant in the Master's in Business Data Analytics program next academic year. And subsequently, we would also love to get somebody, what we're looking to hire is going to be a senior that could work part-time in the spring semester, and then full-time over the summer, like as a summer internship, and then transition back into a part-time role while being enrolled in in the graduate program next academic year. So it would be a graduate assistantship with tuition waiver, stipends during the academic year, and then at an hourly rate in the spring while still a senior, and then over the summer as well. So I'll have all those details. I expect to have the job description created and posted by the end of the week in Handshake. So Brad and I fully intend to send that out to the class for any of you that might be interested in pursuing the master's program after wrapping up your senior year. But this is an opportunity, like I said, that some of you may definitely be eligible for and interested in. So as you are starting to think about, for those of you who are seniors, as you're starting to think about what's next, and if you've even been considering that grad degree, this might also help to sweeten the deal a little bit. So I just wanted to put that on your radar and let you know that more information on that will be coming out by the end of the week, but we're excited about that. And then that's in addition, Kristen serves as my graduate assistant for data driven. I'll still have that graduate assistant position next year, but this is an additional one that we have funded now. So, and that GA position will be specifically focused on COVID data analysis work. So it'll be a bit more targeted. So anyway, all right. Any questions real quick before we get started on that module 6 content? Any questions on that or on anything? I know I've seen a few of you have already submitted assignment 5, but any questions as you all have started working through that? All right, we'll go ahead and get started then. Let me share my screen real quick and we'll go to work, as Brad would say. Okay. And I do have my chat box open too, so I'll try to reference that from time to time to make sure I don't miss any questions. So last Friday, we left off, we started looking at this UN example and looked at added variable plots. So this is still from the regression RMD file. It is in the module 5 content, but we're continuing off of that into multiple linear regression. Okay, so again, you can reference that RMD there in module 5. But just to refresh our memory real quick, we loaded in the ALR4 package and then looked at the UN11 data. So we'll just look at that. We have different countries here, the region, the group, which as Brad was saying, would either be other Africa. We have fertility, PPGDP. And again, if we want to look at the specifics of this, let's look at UN11. Okay. So we have fertility, which is the number of children per woman in that country, PPGDP, which is the per capita gross domestic product within, and that's in US dollars is the unit of measurement there. Life XF is the female life expectancy in years, percent urban. Okay, so those are our different variables that we have and what they all mean. So just refreshing our memory there. So we ran two different models. We created mod 1, which was a linear model of looking at log of fertility given life expectancy for females and log of PPGDP. Again, we took the log of those two values because they were pretty, you know, there was a wide range. So this kind of helped normalize those values for prediction purposes. Okay, and again, we're going to talk about how we can transform different variables a bit more. I'm going to touch on a few of those ways today, and I know Brad's going to go back and hit on that a little bit more on Wednesday. So we did our mod 1 that we looked at, looking at two different variables and their impact on fertility. And we had the summary of that here. I'm not going to talk about it right now. We're going to get into that in a bit. And then mod 2, we just looked at the log of fertility given log of PPGDP. So this was just a simple linear regression looking at one variable. And then we looked at the added variable plots. I'm not going to run that because we're really going to move forward today in just talking about our multiple linear regression models, those that have more than one predictor variable. So, you know, again, I just wanted to kind of refresh our memory of the data set that we have, as well as this mod 1 that we created, because we're going to reference back to that a bit in the discussion in just a bit. So again, this is looking at fertility and the impact that both life expectancy of females and the per capita gross domestic product within that country has on fertility rates. Okay. All right, so let me switch back over here real quick to the HTML version of this because it's going to be a bit easier to talk about some stuff from here. So again, we talked through the added variable plots section, so I'm not going to go through that. I want to talk a little bit about the math behind how these multiple linear regression models work. Now, Brad's the one with a PhD in statistics. He also is one of the few people that I know that can make, you know, talking about math exciting and fun because he's so passionate about it. So I'm not going to spend a ton of time on the math today. Brad will hit on a lot of that again on Wednesday. I'm going to touch on, you know, a basic thing that you need to understand about multiple linear regression right now from a math standpoint. And then we're going to talk about interpretation and look at a couple of examples. Okay. Brad is really good with the concept, teaching the concept. I have a lot more experience in being able to apply those concepts. So that's what I'm going to focus on a bit. But in our multiple linear regression model here, what it's saying is that our expected value of y given x is equal to beta naught plus beta 1 times x1 all the way up to beta p times xp. Okay, and p is the number of predictors that we have. So, you know, if we had 3 predictors, we would have beta naught plus beta 1 times x1 plus beta 2 times x2 plus beta 3 times x3. Okay, or in the example that we're working with right now, where we're looking at life expectancy of females and PPGDP, we would have beta naught plus beta 1 times x1 plus beta 2 times x2. All right, but how do we get to this? All right, so before we talk about the notation and the math behind it, let's also talk about some ways that when we're starting to look at just more than one predictor, we might have to do we might have to look at our variables a little differently. Like for instance, right now we're using, log of fertility and log of PPGDP. That's a way of transforming our variables to make them a little bit more interpretable and modelable. So we do transform our predictors at times. So right here, we're saying sometimes we really would like to say that XJ is our predictor, but it doesn't allow for the setup of linear regression. Because we like the ease and interpretation of SLR and MLR, so simple linear regression and multiple linear regression, we transform the predictors sometimes. So again, in the UN example we just used, we used log to transform that. It allows for more flexibility with the problems that we can use linear regression for. So some different ways to transform our predictors. We have polynomials and interactions. So polynomials represent MLR models where we place X to a D. So, it could be squared or cubed, where D is a term or predictor in our model. This allows for curves to fit our data rather than a straight line. I mean, we've even seen some examples in class where when we just plotted the data, our actual values, we saw, even looking at just two variables, that at times you might think that a curved line would be a better prediction line than a straight line. And that is more common than seeing some sort of a linear relationship. So, adding polynomials to some of our predictors can help. Interactions allow us to use terms xj times xk, which allows us to model for relationships and predictors that we can exploit. So think about, an example given here is BMI. BMI on its own can be a really powerful predictor, which is a combination of height and weight. So again, we can often multiply two predictor variables to create a new one. And I'm going to show you an example of how we can do that in one of the examples I'm hoping to have time to get to today. If not, we'll touch on it on Wednesday. We also have dummy variables and factors. So dummy variables also go by a different name, which is indicator variables. I'll be completely honest, in the practitioner type world, people call them dummy variables 9 times out of 10. But it's a variable that takes on a 1 or a 0. So it's almost like creating a new binary variable. And it's a way to, basically, account for something existing or not. So it's 1 if it exists, 0 if it doesn't. So we'll talk about that a bit more too when we start looking at more binary and categorical type variables. And then principal components. In the real world, we have predictors that are related. And in some instances, they measure the same thing. What principal components allow us to do is create a special form of weighted average of these subset of variables. So if we have several related variables, we may not need all of them. So principal components help us identify the ones we do need to continue utilize for prediction. And there's other methods of that, which again, as we work through this module content, you'll start to see. We're actually going to see an example later today too, because so far, we've given you all examples, especially with simple linear regression, where there is, a level of significance at a 0.0, at a 0.05 level of significance. Our p-value is low enough where we know that the predictor variable has a strong relationship with the response variable, but there's times when that's not the case. So getting down into the math, like I mentioned, going to look at our notation here. So again, we have some key things to know. We have n observations. Okay, so one through n observations. That's the number of rows that we have in our column when we're thinking about it visually from our data frame or an Excel spreadsheet standpoint. But now we are defining that we have p-variate matrix of predictors X. So we have, of all of our columns, that we're going to use. So again, I'm trying to put this in kind of a visual term for you. So if you're looking at your columns as your variables, all of those that you're planning to use as your predictor variables, you have a P quantity of those. Okay, so N is our number of rows or observations. P is our number of columns that we're using as predictors. Okay. And then we have a univariate response Y. So we're just trying to predict one variable, our Y variable. Okay, so we have our expected of Y given X is equal to X times beta. So where we define Y is going to be our response variable for observation 1 through N. And then X, this is where we get into this matrix format, which those of you that have had more calculus, this might, kind of come back and jog a memory, or if you've done it more recently, you may be very familiar with this kind of matrix notation. But for X, we have our rows are our observations. So we have observation 1 through N, and our columns in our matrix relate to the number of predictor variables. Okay, so the 1 here is holding place for what we're going to end up using for our beta naught value, but because we know here, if we scroll back up real quick, if we look up here at our formula that we're using, okay, sorry, this first one here, x11 is going to be equal to our x1 value, but we need a placeholder here for beta naught. So we just put 1 in the first column of our matrix for all of our x's. Okay. So again, going down the rows, you have a row for every observation. You have a column for every predictor variable plus 1. Okay. And then we also define beta as beta naught through beta p for, again, we have a beta for every predictor variable plus our beta naught. So now we can define our multiple linear regression as y equals x times beta plus our error. And error is defined again as error of 1 through n. So this is, we have an error for every number of observations that we have. Okay, and then we get into, we can now denote our mean function at point xy as, okay, so this is xi transpose beta equals beta naught plus beta 1 times xi 1, so forth and so on to beta p times xip. Okay, so this would be the mean, which is our predicted value for our y value at that point. And then variance here looks a little bit different from what we had in simple linear regression, because our variance is going to be equal to sigma squared times I to the n, or sorry, in, which is the identity matrix. And you can see those details here. I'll be completely honest. I just wanted to explain this matrix piece here, because again, we're multiplying our beta naught times our first column here, beta 1 times our second column here, so forth and so on to get us to our equation that we're using. And this is all going to make a lot more sense when we start to interpret our model here in just a minute. Okay. All right, any questions on that and understanding that matrix and how we're going to do our calculations here for our new our model, where we're adding additional predictor variables? Okay. All right, so I'm going to kind of fast forward here a bit. And again, Brad's going to come back and touch on some of the math behind all of this a bit more on Wednesday. I am going to head down here to looking at prediction, fitted values, and linear combinations and how to interpret our model. So I'm going to switch back over to our studio where we can actually run some code, and this is all going to make sense. So let me scroll down and get to where we need to be. And we are going to talk about the interpretation of our model real quick. Okay. All right, so down here, I ran this earlier. We were looking at summary of mod 1, which, to remind you here, is log of fertility given life expectancy of females plus log of PPGDP. Okay, so let's remind ourselves how we interpret this, because I know Brad touched on it very briefly last class, but it's very similar to how we interpreted our simple linear regression models. So here we have our intercept value of log fertility. So this is saying that if life expectancy was 0 years old for females, okay, not realistic, but if that were to be the case, and if log of PPGDP were equal to 0, then we would expect log of fertility to be 3.5. That's, like I said, not a realistic scenario. So this is really just our tuning parameter to say this is our y-intercept. This is our tuning parameter. Now we want to go look at the impact that each of the predictor variables have on fertility. So same as what we said before, for every increase in 1 unit of our predictor, so here we have life expectancy. So for as age increases, life expectancy for females increases 1 year for our country, we expect on average for log of fertility to decrease, okay, 0.02. All right. So it has a negative relationship between the life expectancy of females and the fertility. We look over at our p-value here, okay, really close to 0. So at a 0.05 level of significance, we do see that there is a relationship. Life expectancy of females does have a relationship with fertility. Now with log of PPGDP, as it increases 1 unit, we also see fertility decrease, this time by 0.065. on average, okay? And then we look over here, we still have a very, very low number, not quite as low, but it's still low enough that we know that it is significant. So, I mean, it's definitely lower than 0.05, it's lower than 0.01 as well, if we started looking at different levels of significance. So there is a relationship. Now, one really important thing to note is, even though we're now looking at multiple predictor variables, when we're interpreting our model, we have to state that we're keeping all other variables constant. So let me use life expectancy of female. So if we're going to say that as the life expectancy of females increases 1 year, it's going to have a negative impact on log fertility. Well, we have to keep everything else constant as well. So we're going to say that not only what we would typically say in our interpretation is, and I'll type it down, actually I'll type it right up here before we get into our prediction stuff. Let me scroll down real quick. Here we go. Keeping all other predictor variables constant as life expectancy in females increases 1 year on average, we expect log fertility to decrease 0.02 units. Okay, or I guess 0.028 units. Okay. The other thing for the purposes of this class, don't feel like you have to convert log fertility back to just fertility. For these examples and for these purposes, you can just keep it in the generic units measurement just to make your life a little bit easier. For some of the other examples that we'll be doing, we won't have to work with log values, but for the purposes of our class and stuff, this is absolutely fine to do. Okay. So again, this is the one little key addition that you're going to see when you're interpreting multiple linear regression models, is this keeping all other predictor variables constant piece. Okay. Now, another thing that we want to take a look at is our multiple R squared. So remember, with simple linear regression, we said that, that one variable could account for, that percentage of variance. It could explain that percentage of variance. So now what we're able to say in this example is that combined life expectancy of female, knowing the life expectancy of females in the PPGDP, we can explain 69% of the variance. Okay, that's pretty good. There's a good chance if we added in additional variables, we could explain even more. But again, that's pretty good. And that's what we're taking away from that value right there. Okay. So interpretation still doesn't change too much looking at multiple linear regression compared to simple linear regression with that piece. Now, let's go look here at our how we're going to look at our confidence and prediction intervals when we get into multiple linear regression. Okay, our code is going to be very similar. We're going to predict using mod 1. Okay, so I ran mod 1 earlier, so that is stored in my environment and I can reference it. And we're going to see what our prediction would be if we assume life expectancy to be 76 years old and PPGDP to be $14,690. Okay, we'll look at both our confidence and prediction intervals and take a look at how we would interpret that. So first we have our confidence, and then we have our prediction interval. So what this is saying, okay, again, we're going to interpret it the same way as we do with simple linear regression. So we are predicting that for a country with a 76-year life expectancy for females and a $14,690 PPGDP, we are predicting that their log fertility is going to be 7.73, okay. But on average, we're 95% sure that on average, because again, we did our confidence interval first, we're 95% sure that on average, that log fertility is going to be between 0.69 and 0.78. Okay. We're predicting, again, that log fertility for that country would be 0.73 with 95% of our observations with that life expectancy and PPGDP to fall somewhere between 0.24 and 1.22. Okay, so same interpretation we saw there with simple linear regression. One key thing to note though, when we look at transforming our data, okay, and in this case we used logs, when you go to run your confidence and prediction intervals, notice how I set just PPGDP to the value I wanted, not log PPGDP. Okay, this is one really important thing to note. You want to make sure that you are referencing, you're plugging in values for your original predictor variables that existed in the data frame that you would have used to model on. Otherwise, you're going to get an error and or really skewed results. Okay. All right. Any questions on that? I'm going to take us to a little bit of a different example where we're going to start to see a little bit different things, and we will be able to talk in things other than logs that will probably make a little bit more sense. Okay. So let's look at another example here. This is going to look at even more variables than what we were just looking at. We're going to look at more than just 2 predictor variables. This is in the ALR package, so I'm going to go ahead and load that in. And we're going to use data fuel 2001. And let's go ahead and check out what all Fuel 2001 has to show us. Okay, so this is data on motor fuel consumption and related variables for the year 2001. The unit is a state in the United States or the District of Columbia. So basically we have a row for every state. Okay, and we're going to see that here in just a minute. This data frame contains the following columns. We have drivers, so number of licensed drivers in the state, fuel C, which is gasoline sold for road use in thousands of gallons, income, which is per capita personal income. Again, this is for year 2000 because they would have had that information from the year prior to when this was collected in 2001. Miles, which is miles of federal aid highway miles in the state. MPC, which is estimated miles driven per capita. POP, which is population age 16 and over, so those eligible to drive. And tax, which is gasoline state tax rate, cents per gallon. Okay, so let's look real quick at the head of our data to get a better feel for it. So here we see over here, we have, this aligns with the states, so they're using state abbreviations there. All right. Just a sec. Let me make this a little bit smaller so there we go. So you guys can see everything. All right. What we're going to do though is this is where all that transformation piece comes into play. So in this example, we want to look at additional calculations and create some new variables. So what we're going to do is rename our data frame and add some new columns. So transform is the function we're going to use. Now I will say we could use the dplyr package. Some of you have had some familiarity with that, and Brad and I of course introduced it, but we could use our dplyr package to do the same thing in a little bit of a different way using the mutate function. But this is a way to use it with base R, which is, you know, the formulas and the functions that exist in R standalone as it is. But we're gonna use a transform function to take our original data frame of Fuel 2001 and basically overwrite it to include additional columns. So now we're gonna have this D-lice, which is gonna be equal to 1,000 times the drivers per population. So total number of drivers divided by the total number of eligible drivers, because again, our population is 16 and older. So in theory, you know, anyone 16 and older is eligible at least to have a driver's license. And then we're multiplying it by 1,000. This is also because of we're trying to basically normalize everything. So we're going to do 1,000 times our drivers divided by population. And then for fuel, 1,000 times fuel C, which again is gasoline sold for road use in thousands of gallons, divided by the population. Okay, so this is looking at basically fuel consumption per the population. So again, it's normalizing it. And then we have income, which is it's going to overwrite our pre-existing column of income instead of creating a new one, where it's going to be income equals income divided by 1,000. Okay. Just so you know, too, there is a note here in the help section that talks about, this comes again from ALR, advanced linear regression. I know Brad's talked about that textbook before. There's a free version of it. He uses a lot from it. This is a data set that's used quite frequently, and this transformation is recommended pretty consistently before doing any sort of modeling. Okay, so we're going to go ahead and run that real quick just to update our data set and look at our new variables here. So you can see we have a couple of additional columns, and our income column just got overwritten with that new calculation. All right, we're going to do a model now to look at fuel given tax, driver's licenses, income. We are still going to use log of miles again to help take that wide range of values and bring it to a more normalized value. And our data is going to be equal to Fuel 2001. So we'll run that, and we're going to look at the summary of that. Okay, so here we have our summary, same as what we've had before. Okay, first thing right off the bat we're looking at is the intercept value of 154.19. So that's saying if we lived in a state where tax was 0, driver's licenses were 0, income was 0, miles were 0, then, you know, we'd expect fuel, our fuel consumption per person to be 154 gallons. Probably not a realistic scenario. Can't imagine a place where that would be the case. So again, this is a tuning parameter for us. Okay. I promise there are occasionally scenarios when this could, when this intercept value could exist, because I know every example we've given you so far has set up, this is just a tuning parameter, but I will say 99% of the time it's a tuning parameter. All right, then we go down and we look at tax and the impact that it has. Again, big difference here with multiple linear regression, holding all other predictor variables constant. We see that with one increase in tax, like 1 cent increase, because again, I'm looking over here, gasoline state tax rate in cents per gallon. So if tax is increased 1 cent, we expect the fuel consumption to decrease by 1 unit. Okay. And fuel was a new one that we created by dividing gasoline sold for road use in thousands of gallons divided by population. Okay, and then multiplied by 1,000. So this does give us gallons per person. So we would expect as tax increases 1 cent, the per person fuel usage would decrease by 4.2 gallons. That's how we would interpret that on average. Never forget the on average. Okay. All right, and we're looking over here at our p-value. Now look, we're starting to see some changes here. We're used to seeing 3 stars. We're used to seeing values really close to 0. This is starting to look a little different. In fact, if our level of significance that we were measuring against in this particular problem were 0.01, okay, if it were 0.01, this would not be a significant predictor. Okay, so we may opt to throw tax out the door. It's not having as much of an impact on our on fuel consumption as some of these other variables do. Okay. Now, again, for our purposes right now, we're just focusing on a 0.05 level of significance. And Brad and I will be sure to make it very clear if we want to look at a different level of significance. Typically, it's going to either be at a 0.05 or a 0.01 level or both. But that would be something worth noting is, you know, if we were at a 0.01 level of significance, then tax does not have a strong relationship with fuel consumption. Okay. And then for driver's licenses, for 1 unit increase, so for every 1 person that gets their driver's license, we expect on average to see an increase of 0.47 gallons of fuel consumption per person. Income has a negative impact. So as the per capita income increases, we would see fuel consumption decrease 6.1314 gallons per person on average. Okay, and these still at a 0.05 level of significance and a 0.01, we're still safe here. Okay, there's still a level of significance for all 3 of these variables here. Okay, but that tax one is one we want to keep an eye on as we continue to model with this data set. And then here we see for our multiple R squared, only 51% of our variance can be accounted for using these variables: tax, driver's license, income, and log miles. Okay, not a whole lot. So definitely in this model, there's some things missing that we might want to account for, or maybe further ways we want to transform our data or look at different relationships there. Again, we're going to get into some of those methods the rest of this week and next to show you how to account for that. Okay. Let me open back up the HTML file. And we'll talk through some of what we're seeing here. So, you know, with these multiple linear regression models, it's hard to plot, you know, it's hard to plot and show the relationship of all of those predictor variables and the response variable. What we can do is look at the effect that, you know, one of the predictor variables would have in our model. So, you know, I could go back down here and run this, but if we were to just plot the effect of tax in our fuel model that we set up, this is what it looks like here. Okay. We can say, can we say that a higher tax rate, so taxes here along our x-axis, causes lower fuel consumption? No, I mean, we know that not to be the case. We've observed states with higher tax rates. Yeah, they have higher tax rates, but do they have lower fuel consumption? I mean, some do, some don't. It just varies. So we can say that there's an association, but we can't infer causations. That's what you'll hear us talk about a lot. We talk about relationships that exist and some correlation that might exist, but certainly, causation is a lot more difficult to prove. And again, we'll talk about that a bit more later. So also in the example, and we just talked through this, signs of our estimates. Again, in a lot of what we've seen a positive relationship. So our values down here are typically positive numbers. We're starting to see now some negative values, whereas whereas our predictor variable, if it increases, it's going to have a negative impact on the response variable. Okay. So just be really, really very careful to pay close attention to that as you're working on interpreting your models. All right. Let me see here. Let's go ahead. I think I want to stop there. I think I'm gonna, yeah. I know we're gonna be done a few minutes early today, but I think I want to stop there to let that sink in, because really, like we talked about today, the differences between simple linear regression and multiple linear regression from an interpretation standpoint, there's a lot of similarities. The biggest thing is adding into that interpretation that, keeping all other predictor variables constant. Okay, so this doesn't allow us to look at what happens if there are changes in more than one predictor variable at one time, which is probably a more normal occurrence than otherwise. But what we can do is use the predict function, and plug in different values for all of our predictor variables and see what kind of confidence and prediction interval we get back. But from an interpretation standpoint, we're just looking at the effect one predictor variable has at a time on the response variable. Okay. I think we'll stop there before we get into any more examples. That way Wednesday we can touch too on some more of the math behind all of this, and then we'll get into some more examples. And we'll start looking at, we'll start getting into examples later this week too, where we'll see variables that aren't significant at a 0.05 level of significance, and how we choose to handle that, because we often have different options of how we do that. And there are also some different functions that make looking at that a bit more efficient as well in R. Okay. So any questions real quick before we wrap up for today? I'll go ahead and stop sharing my screen. Okay. All right. Well, you guys have a great day. Enjoy an extra 5 minutes of your Monday, and we will chat again on Wednesday.